We will now examine the effect of overpotentials in our electrochemical cells. In order to do this, we need a first quick recap of the overpotential. So remember we said that the overpotential is simply the difference between the equilibrium potential and the actual potential at an electrode. So it's a fairly simple quantity to measure. We apply this overpotential from an external source. So we connect a potentiostat and drive this potential through an electrochemical cell. This overpotential is what we need to drive a current through the cell. So if we simply apply the equilibrium potential, we're not likely to drive a particularly high current. We need to drive a higher potential in order to overcome the kinetic barriers to the electrochemistry going on in our cell. Remember that we said a lower exchange current density, the slower the rate at which electrons are exchanged at equilibrium, the higher the overpotential we need to drive a current through the cell. We're going to first look at galvanic cells. So remember, a galvanic cell is one that we simply put electrodes into the electrolyte and the cell potential drives electrons through the external circuit. So let's consider the cell here where we have copper and silver present in the cell. So this cell potential we can calculate under standard conditions would be about plus 0.46 volts. Under galvanic conditions we would expect to have a reduction at the silver electrode. So we have the silver ions being reduced to silver metal, and at the copper electrode we would expect to have oxidation where we have the copper metal going into solution as copper ions. But what we're really interested in with the galvanic cell is as it's doing work, as it's driving the current through the external circuit, we want to know how does that potential vary as the current flows through the circuit, and what can we get from this information. A key factor in our galvanic cells is the performance of the cell with the overpotential present. So whenever we apply an overpotential to a cell, remember we get a different cell response. With a galvanic cell, the one that we were looking at, the copper-silver cell, we said that we would have reduction at the silver electrode. So we would expect to observe, in this case, we would expect to observe a cathodic overpotential. So we have the cathodic current, or the reduction current, running for a given cell potential, while we would have oxidation at the copper electrode driving an anodic current. And the overall current we see, if you remember the Butler-Volmer that we looked at before, the overall current is the sum of the reduction and the oxidation currents. The current voltage profile is shaped fundamentally by the Butler-Volmer equation, so the shapes of these curves are exponential in nature. But remember, this is a galvanic cell, so the passing of current is spontaneous. It's a spontaneous process as this cell strives to reach equilibrium. So let's now look at what happens in that cell as we allow that cell to pass the current. If we now connect a potentiostat which allows us to control the potential on the cell, we can hold the cell at a particular potential. So let's hold the cell at the copper potential. If we do this, no current flows. This copper will be at equilibrium, no current would flow to the cell. However, if we then release that potential, if we then allow current to flow freely under the thermodynamics of the cell, the spontaneous change causes the potential to increase, to become more positive, allowing oxidation current to flow at the anode, and we establish an equilibrium position. Conversely, if we were to change the potential and hold the cell instead at the silver equilibrium potential, again, no current flows. But if we then release that potential and allow the cell to drive current again, spontaneous change will cause the potential overall to decrease and become less positive. Again, allowing a reduction current to flow at the cathode and establishing that equilibrium. When we consider the galvanic cell delivering energy, we think of it delivering a current. But its ability to deliver a current, the amount of current it delivers, fundamentally affects the cell potential because of the need to drive this overpotential. If we think about our overall cell potential, we have our equilibrium cell potential for copper and our equilibrium cell potential for silver. Remember, these are the standard electrode potentials that we can look up in books, and we would expect the overall cell potential to be the difference of these, and we should be able to measure this. However, by allowing the cell to equilibrate, we will actually get a different potential measurement from that which our predictions would give us. As the cell runs, the concentrations change, so we move away from ideality. We have an irreversible process. We might lose material, which causes the process to be irreversible, and the cell itself has a fundamental internal resistance. So in order to identify how the cell potential varies with current, we need to find the potential at two equal and opposite currents. So if we define two currents, we find that in order to drive a particular positive current, we need a particular anodic potential, and in order to drive a negative current, we would need a particular cathodic potential. What this gives us overall for a given current, we find the difference between these new potentials driving these currents, and we can extrapolate this to find the actual measured cell potential for this current. As the current increases, the cell potential drops. We only obtain the thermodynamically predicted cell potential under zero current conditions. As soon as current starts to flow, we start to deviate from that equilibrium position. What happens then with an electrolytic cell where we are driving the current around with a potentiostat? So let's consider the same cell again. We understand how it works under galvanic conditions. Let's look at it now under electrolytic conditions. This time we're going to impose a voltage to drive the cell in a non-spontaneous direction. So we're now going to drive the reduction at copper instead. So we now bring copper 2+ to copper metal, and we drive oxidation at the silver electrode. So the opposite way around to what we had with the galvanic conditions. Now we want to think of how does the current vary with the applied potential. And again, what can we gain from this new information? Once again, we want to look at the cell performance and how that varies with the overpotential again. So as we say, it does still vary. So let's look at the current voltage curve again. This is a familiar shape. We've already seen this in terms of the Butler-Volmer kinetics we looked at before. But now we're looking at a much greater potential range, the potential under which we would expect to do real electrochemistry. Now remember we said that we'd have reduction at the copper electrode. So we have reduction here of copper ions going to copper solid. At the copper equilibrium potential, no current flows. Okay, so if we're holding our cell here, we wouldn't expect to get a current. So in order to drive the current through, we have to drive a more negative potential. We have to move the potential to a more negative value. Conversely, at the silver electrode, if we hold the cell at the silver equilibrium potential, again, no current would flow. We have to apply an overpotential to overcome the electrode kinetics so that a current can flow. Again, the curves are still derived from Butler-Volmer kinetics, so are still fundamentally exponential. Remember, we're driving the cell against spontaneous change. So in this case, we're forcing copper to be deposited rather than copper being released into solution. But in order to drive a cell at a particular current, we have to drive a different potential than we predicted. Again, remember, the difference between the standard potentials would be expected to give us our cell potential, but in order to get a measurable current, we have to apply a much greater overpotential. So we apply the same principles as for the galvanic cell. We identify a current required, so we identify our anodic and cathodic components, and the applied voltage that we need is once again the same separation from the tie lines as we found before, meaning that we have to apply a much greater potential in order to drive a current through that cell than thermodynamics would otherwise predict. When we compare the galvanic and electrolytic cells, we can always use thermodynamics to predict the cell potential. However, when we actually come to do measurements, we find that the output potential of a galvanic cell is considerably lower than that predicted by thermodynamics, while the charging potential of an electrolytic cell is considerably greater than that predicted by thermodynamics. No matter which cell we're looking at, the measured potential varies with current. So depending on what current is being driven through the cell or the cell is supplying, we would expect to measure a different potential coming out of that cell. So for a galvanic cell, the effect of the overpotential is to reduce the output of the cell from that predicted by the Nernst equation, whereas with electrolytic cells, the effect of overpotentials is to increase the applied voltage required to put a current through the cell. We always have a struggle between kinetics and thermodynamics. Thermodynamics predicts overall outcomes for our reactions, for our cell potentials, for everything in chemistry, while kinetics says how fast something happens. So if we consider a particular cell where we've dissolved zinc chloride in a solution at 10 to the minus 2 molar, and we maintain the pH at 7, we would expect to see these cell potentials. When we look at this couple, we can see that we have two possible reductions happening. We can either reduce H+ to hydrogen gas, or we can reduce zinc 2+ to zinc metal. So more than one outcome can come out of this cell. So are we going to reduce zinc, or are we going to reduce hydrogen? If we look at the current voltage curves, again, and we think about sweeping our voltage to negative potential, so we start our voltage at 0 and we drive it to negative voltages, we would expect to see hydrogen evolution happening once we get to a potential of minus 0.414 volts. So as we come into this region here, we start to apply the overpotential, and we would expect to start seeing hydrogen evolution, while we would expect to see zinc if we drive it further past the zinc electrode potential. But the result that we observe depends fundamentally on the electrode material we're using. So depending on the value of the overpotential required to deliver a particular current, we may see a different result. So let's look at what happens once we start varying the electrode potential. Let's consider platinum and mercury electrodes. If we look at the exchange current densities for each one, for the hydrogen couple and for the zinc couple, we can see there's a big difference between the exchange current potentials for hydrogen, whether we're at the mercury or the platinum electrode, while for zinc it's largely unchanged. It's still a very high exchange current density. So let's consider platinum first. Let's look at platinum, where hydrogen has a moderately high exchange current density. So zinc reaction has fast kinetics, it has that high exchange current density, we expect to see fast kinetics going on. So we would see high reduction currents near the zinc equilibrium potential. The hydrogen is also fast, it's also relatively fast. We might need a slightly higher overpotential required, but we can still drive a current through the cell and see hydrogen production. So as we sweep our potential from zero down through the hydrogen potential, we start to see hydrogen production at the expected voltage. This is an expected result and something that shouldn't worry us too much. Let's, however, now consider mercury electrodes. The equilibrium values are unchanged, but we've now gone into a situation where hydrogen has very poor kinetics. So we've got a very, very small, we've got 9 orders of magnitude difference in the exchange current density, so very poor kinetics for hydrogen. What that means is we require a very large overpotential to drive a current. And what that means is the overpotential we have to apply is considerably greater than that for the zinc couple. The overall result of this is that because the zinc still has fast kinetics and only requires a small overpotential, predominantly at the mercury electrode, we would expect to see the zinc reaction first. The effect of these electrode kinetics can't be ignored, so depending on how we design our electrodes, how we design the material that we're working with, we can tailor our exchange current density to get different results at the electrode. An example of this is the chlor-alkali industry, where we electrolyze sodium chloride solution, or salt water. I'm not going to go into too much detail about it because it's a standard A-level case study, but fundamentally we have 2 electrodes, our cathode and our anode, each which has a competing process. The cathode processes center around the reduction of sodium to sodium metal, or the reduction of water to hydrogen and hydroxide. When we look at this, we see that we have a huge thermodynamic barrier to overcome to reduce sodium, while our barrier is not quite so great for the reduction of water. However, if we look at the anode processes, the electrode potentials are very similar, so we now need to think about the kinetics of what's going on. Looking at the thermodynamics, we would expect to see a lower barrier for the oxidation of water to hydrogen and oxygen than we would for the oxidation of chloride to chlorine gas. But when we look at the exchange current densities at the electrode, we see that the kinetics for the chloride oxidation are considerably better. We have a much greater exchange current density than we have for the water at that electrode. So thermodynamics predicts that we should get hydrogen gas and oxygen gas as products from this reaction, because we have a lower electrode potential for each one, so the thermodynamics predict it. However, when we look at the exchange current density as a function of the applied potential, we see that the exchange currents of that platinum electrode affect the outcome of the reaction. Because of the much, much smaller exchange current density, we require a very high overpotential for the oxygen-water couple. And we see that we need to apply very, very high overpotential to supply any measurable amount of current to actually make that reaction proceed. If we look at chlorine instead, we find that for the same potential, we get a much greater current happening with the chlorine, so the chlorine production dominates. To summarize, we need to remember that electrode processes fundamentally affect thermodynamic predictions. In a galvanic cell, we see that the actual cell potential is considerably lower than we would otherwise expect, while for an electrolytic cell, the cell potential is higher than we would expect because of the overpotentials required to drive a current through the cell. The value of that cell potential fundamentally depends on the magnitude of the current. So if we have a high current, we would expect to see a lower galvanic cell potential, whereas if we drive a high current through an electrolytic cell, we would expect to see a higher cell potential required. The effect of faster kinetics also can't be ignored. Faster kinetics can favor adverse thermodynamics. If it forms faster, we will get more of it happening. Through modification of our electrodes, we can increase the exchange current density, which will favor particular processes to our advantage.